afternoon, everybody. Esteemed guests and participants, on behalf of CRTDH Gandhinagar, I welcome you all. In the Conclave 2023 DSIR, supported by Index TB, SSIP, Naroda Enviro Private Limited, and Rasayan Private Limited, Viksit, a step towards Viksit Bharat Abhiyan, empowering MSMEs and startups. Thank you all for joining us. Today, we have a diverse and engaging agenda planned for our time together. Our discussion will encompass a variety of topics aiming to showcase Department of Research and Industrial supports through in supporting technology, scientific research, support and access to specialized services to MSMEs and the Common Research and Technology Hub, that is CRTDH. Now we will be delving into the workshops, flow synthesis and continuous workshop. And we having two esteemed speakers today, Dr. Amol Kulkarni and Dr. Anil Kinage. Before inviting the speakers, I would like to introduce something about the speakers. Dr. Anmol Kulkarni is a Chief Scientist in Chemical Engineering and Process Development Division at CSIR National Chemical Laboratory NCL Pune since 2005. He holds a background in chemical engineering and he did BTech in engineering in 1998 and a PhD in chemical engineering in 2003. Dr. Kulkarni has impressive and international research experience, including a postdoctorate from MPI Madburg in Germany and a Humboldt Fellow. A stint, he is an IUSSTF Research Fellow at MIT in USA 2010. He has been awarded prestigious Shanti Swarup Bhatnagar Prize for Science and Technology and one of the highest Indian science awards for his contributions to engineering sciences in 2020. His primary research focused on microreactors for continuous synthesis of pharmaceutical intermediates, dyes, perfumery, chemicals, and nanomaterials. He has established India's first microreactor laboratory. He has received several awards and recognitions, published numerous papers, holds multiple patents, and actively contributes field through editorial roles and industry consultations. So I welcome Dr. Anmol Kulkarni to please, sir, I invite you, please enlighten us.
I am, thanks to Professor Chinmay for inviting me for this Pre-Conclave workshop, and thank you everybody for kind of missing the India versus South Africa match and coming here for this program. My name is Amol Kulkarni and not Anmol Kulkarni. So, she was spelling Anmol Kul. So, okay. So, let me begin. What I am going to do is that I had actually planned for almost close to 3 hours of session that Professor Chinmay has told me. But what I will do, I will try to kind of little bit shrink it because prefer to have more discussions after this rather than spending too much time. But what I will do, I will kind of out of a large number of different sections on flow chemistry which we typically conduct as a part of training, I have just selected 2 or 3 which I will just do here and show you some successful case studies at the lab scale and at larger scales and so on to give some confidence. So, with me my colleague Dr. Anil Kinage is also here, who works on high pressure hydrogenation in batch as well as in continuous mode. We conduct this kind of and little elaborate training courses every year in NCL for a period of almost 6 days, 6 full days, and the purpose is to make sure that we kind of people can have money to buy equipment, people have money to buy, create facilities, people have right kind of examples to choose when you want to transform something from batch to continuous. But what you do not have is people who are trained to kind of operate those things, or people who will think what can be made continuous and what cannot be made continuous. So, this is an attempt where we kind of try to educate that many times, because in the lab when people do some chemistries, the typical chemist is not trained to think outside the round bottom flask. They do not like when I say this, but they do not think outside the round bottom flask. We are very much kind of moment you change them, when you tell them that reaction can happen anywhere, moment the reactants can come together, they do not accept that easily. It is because for years and years they have spent their time doing the reactions in on bottom flask and the test tubes and beaker and so on. So, the idea is to basically give that change that mindset. So, for some of you who do not know NCL, we are a premier CSIR lab in chemical sciences. We have around 6 divisions: catalysis, polymers and materials, organic chemistry, biotechnology, computational chemistry, and all of these have the interface with the chemical engineering and process development department. We are around 120 scientists, 500 PhD students and close to 300 project assistants, and we work with lot of industries, small, medium, large, micro, etc. Size does not matter. So, we publish a lot, file a lot of patents also. So, there are a lot of people who do a lot of basic research and a lot of people who do a lot of applied research. It is a lab where things are balanced properly, because many times you just can't run around kind of repeat the same reactions again and again, but you would also like to spend some good time why it is happening, why you are not getting the required kind of results. So, there are a set of people who just do that part, they do not get into application, but they know why some reactions happen that way. So, in our group we basically do a lot of training programs, and one major part is on continuous processes. Now, why continuous? It is easy because our digestive system is continuous, we think continuously. When we want to travel from any part in Ahmedabad to any other part, we do not want to have traffic jam, we do not want to have speed breakers, we do not want to have signals, we would like to travel continuously, we would like to have, but that is the case with every city. Fortunately, our heart works continuously, kidney works continuously, it is all continuous because it is efficient. And so, when so many examples are around, then why chemical synthesis also should not happen continuous mode? It should be a continuous process, need not be everything need not be continuous, but wherever required it has to be continuous. There are a lot of advantages of that, I will come to those points little later. And it is not that we do not know continuous things, we eat lot of cookies, breads, biscuits, everything which is manufactured in continuous mode. The assembly line in the automobile industry is continuous, pharma tableting happens continuously. So, it is kind of there are successful examples are around, except in the synthesis of fine and specialty chemicals, intermediates and so on. Bulk chemicals are all manufactured in continuous mode, and this is not new. The making chemistry continuous started almost more than 2.5 decades ago for the fine and specialty chemicals and for reactions which are sensitive. Like initially it all started with every reaction to be made continuous, making automated synthesis platforms. Then after that, because people started realizing that while every reaction can be made continuous, you cannot really achieve something. Excuse me, I request everyone not to take photographs, I will share some slides with Professor Chinmay. Thank you. So, people started doing the reactions at conditions which were otherwise not possible, because lot of a new avenue opened where the reactions were usually done at -78 can be done at 0 degrees. You imagine the amount of utility that you are saving, amount of time that you are saving and so on. But then eventually they realize that you are spending lot of time not in the reaction, but in the workup. So, which means that your purification also has to be made continuous. So, just not the reaction. So, your continuous extraction, continuous distillation, continuous crystallization all has to follow. Then followed by that, scale up came into picture, because then when it was seen that all these reactions can be made continuous at small scale, people started realizing that it will be useful if they are made kind of at large scale also. And then manufacturing also started at several locations across the world for variety of types of reactions. Even there are plants, chemical plants, or I would say manufacturing single machine plant by Novartis. It makes a drug called aliskiren. Reactants, 6 reactants go in, and what comes out is a tablet. It makes not only that, the intermediates, the further reactions, the final drug molecule with or purification of GMP grade, all the FDA approved drug molecule comes out, gets added to excipient also continuously, and eventually what you get is a tablet of the out of the entire plant. And one single plant makes 48,000 tablets per hour. So, you can imagine kind of, and it all sits on half of this podium, and they have 6 such manufacturing plants at 6 different locations. So, this is the way people are working. There is value in that, because those drug molecules are also expensive. So, they can put that money in the beginning and earn as much money as possible. but it is also true for the fine and specialty chemicals and intermediates as well. So, as the field evolved, lot of books came out on the subject. It is still growing, there are dedicated journals for this, and which clearly indicate that the field has a relevance. And then there are a lot of such reactors that you must have seen in various exhibitions and at various business shows and all, where you see various kinds of flow reactors which are used. And even some automated platforms like this, here this unique Unixsys system or VaporTech systems, which basically it is automated synthesis platform. You do not need a chemist after you buy this, because you said what reactions you want to do at different temperature, different pressure, different residence time, and then you do not need a person. Machine does everything, gives you the sample, does the analysis, and decides also what next experiment should be done. So, as of now, almost more than 100 industries in India have this kind of a unit, but probably 10-15 use, rest all they do not have people who can use it. And so, it just did not remain restricted to small scale and 1 or 2 molecules, but complex molecules also were also synthesized as the field evolved, and lot of really complex pharmaceutical molecules, deuterated drug molecules, all were synthesized in continuous flow. Like this one example at the bottom here, this is for a drug called Rolipram, and if you see here, there are kind of five fixed bed reactors, 5 different catalysts being operated with kind of inline purification systems, and you go from one end to the other end absolutely seamlessly without kind of any complications. So, you have got all fixed bed reactors being operated at different conditions for different reactions, and you get the pure drug Rolipram at the end. So, there are many such successful examples have been shown, and kind of many such things exist in the literature even and in commercial scale, where people have gone to the really large scale reactors, like the reactors which have a capacity of somewhere close to 600 liter volume, and the reaction time is 3 minutes. So, every 3 minutes 600 liter volumes is processed. So, imagine what is the throughput for the entire day, and that 600 liter reactor actually speaking sits on this kind of a podium. It is a really compact one, but offers very high heat transfer area. So, over the period of time, lot of industries have gone into this, lot of good publications came out, and after that the European chemical industries came out with a plan that they want to basically transform the way they make the chemicals in different segments, like R&D. They thought that by 2004 almost R&D of all the European chemical industries will have flow reactors, then screening will happen, and then industry will adopt quickly, biotechnology transformations will happen, and then fine chemicals and energy production and mass chemicals. This was kind of very quite ambitious, because it was made the entire this kind of a timeline and roadmap was made by the chemists without realizing that there are a lot of engineering challenges that they are going to face. And then eventually it took quite some time, and probably they are still here somewhere. This is happening in US, energy production by companies like Velocys at very large scale. There is a company called Atmonia in Iceland, which Atmonia stands for atmospheric ammonia. They do ammonia synthesis at atmospheric temperature and atmospheric pressure, rather than the Haber-Bosch process, which is at 250 bar at very high temperature, almost 400 degrees centigrade. So, they use nitrogen from air and hydrogen from water at room temperature to make ammonia. It's all continuous process. So, over a period of time, they also kind of lot of consortiums came out where the industries came together. It was not academia. Industries came together. Like, say for example, if you see here this particular case, here kind of 34 members from pharma industries came together in France and some European companies to kind of develop eco-friendly industrial processes. Similar is the case with here again Impulse, integrated multi-scale process units with locally structured element, 20 partners from 7 European countries. So, industries came together to solve the common problems, rather than one company solving problem keeping it to themselves, because it is not going to, at least in India it never happens, people hop. So, you lose the process that way. So, rather than that, the way pharma companies did, many years back there was a big program called LAZOR, L-A-Z-O-R-E. Each alphabet stands for one company, like L for Lupin, A for Arbindo, Z for Zydus kind of. So, these companies came together to solve one single problem of solvent recovery. because in pharma solvents are used in large quantities in the end stage chromatographic applications. They wanted to recover almost as much as possible. So, they realized that there is no point in they spending individually a lot of time and energy into that. They all came together to form a consortium and solve the problem once and for all. In 4 years, kind of each industry, so there are 6 major solvents which they were using. This consortium solved the problem to recover all the solvents to 96% in one single go, and they basically informed everybody, and there was a technology partner who made sure that the plants are put in each plant, each of these locations. So, I think that is what needs to be done. So, people do trust each other when we also need to do the same thing. And typically when you look at the reactions, chemists will always look at what is the type of reaction he or she is doing and what is the reactant, what are the reactants, what are products, etc. Engineers will always look at this part. What are the conditions at which these things will happen? Temperature, pressure, pH, concentration, rate of reaction, then properties like viscosity, density, is it two phase and so on. But so in batch it does not matter, because conventionally a chemist will develop a batch protocol, hand it over to a tech transfer team who will exactly try to follow the same protocol without thinking much about that, and then it will be implemented at large scale. But when you have the processes where the reaction rates get enhanced significantly, like imagine you are doing a reaction at minus 40 degrees centigrade for 8 hours, and in a reactor which is 1 meter cube or 10 KL reactor for 8 hours, instead of that, if you do the same reaction at 0 degree centigrade, what is going to happen? As per the reaction kinetics, with every increase in the 10 degrees, reaction rate doubles. So, at minus 40 it was needing 8 hours, if you do it at minus 30 it will need 4 hours, minus 20 2 hours, minus 10 1 hour, 0 degrees 30 minutes, you keep on going to 20 degrees and so on, you will come to few minutes time. But what is important here is that as the reaction time decreases, the amount of heat that will get generated is not going to decrease, it is going to remain the same. So, you have to handle that much heat in such a short time, and that is where the flow reactors come into picture, because your large batch reactors do not have sufficient area to remove the heat, and so flow reactors which offer 1000 times higher heat transfer area will allow you to kind of generate that much amount of heat. That is where the chemists and engineers have to work together when it comes to making anything from batch to continuous. So, typically when we do a 5 days training course at NCL, we have a little long elaborate program, like day 1 is basics of reaction engineering and multi-phase flow, because when I said lot of industries do gas liquid, liquid liquid reactions, and every day the morning half goes in the lecture, second half goes in doing the experiments based on what you have kind of done in the first half. Then the second day on flow chemistry, various successful examples from the literature, and in the second half and what kind of experimental setup is required for liquid liquid reaction, gas liquid solid reaction, and in the second half people are given all the components required to assemble the setup. So, each team assemble their own setup to carry out their own reactions. So, that is the way second day goes. The next day we actually cover a session on batch to continuous transforming. What should be the approach? How do you check the mass balance, energy balance, multiple case studies, what to avoid, what not to avoid, and so on. And then we go for scale up. How do you go for scale up of this? And in the afternoon they actually start doing the reactions. So, we will pick up one case, either nitration, diazotization, hydrogenation, oxidation. Fourth day again continuous separation, purifications, and these different types of special topics in chemistry. They will continue to do some more reactions in the second half. On the fifth day it is more or like question answers, and again they will do kind of, and since each team build their own setups, when the setup does not work, they themselves know why it has not worked, because they have assembled, so they have to start from the scratch again. So, this goes on for 6 days, and at the end of the 6th day we are sure, and they are also sure, that given any reaction they will be able to do the reactions in their labs, and we give the setups to them so that they can carry it with them, because one of the common excuses are like हमारे पास कुछ नहीं है when they go back and the priorities change, but then that does not happen. We tell them what all they need at the end. What I am going to do today, I cannot conduct that whole thing. I am just going to give some information on batch versus continuous, why it is required, and then I will go back straight to this flow chemistry basics and some successful case studies. that will be better, and then my colleague Dr. Anil will cover some hydrogenations. Okay, so before I begin, long time back in 2012 in OPRD there was one editorial by Professor Trevor Laird, who basically said that although lot of APIs for the generic drugs are cheaper, 78% of them are actually manufactured outside India and China. Okay, 78% of the important ingredients for APIs are actually manufactured in these countries, UK, Germany, Switzerland, Italy, Canada, etc., where the labor and cost overheads are high. They can still compete on the cost as well as because those syntheses are complex. But when overheads and the labor cost in India and China also increase, will we be able to make even that remaining 26%? That is the question he asked. And then he says that only those who are the most innovative and have the most highly qualified and well trained chemists and engineers will be able to survive as the market demands lower and lower prices for generic drugs. So, it means that your prices will keep on falling unless your technologies are become better and better, you will not be able to meet the requirements at all. And so he said that innovative low volume continuous processes might also be applicable in the generics field. Of generics means the large volume pharma drug molecules. When he talks about that, it means that even for the other fine and specialty chemicals it is equally applicable. So, we have trained almost people from 60 different industries over a period of time, and many of them are from this, we are closely associated with many industries, we have trained their people indirectly, directly and so on. This is still a small subset of this thing. Yeah. So, before I begin, the same person in another editorials wrote, companies always measure the cost of doing something, but they will never measure the cost of not doing something, especially not training their staff for new tools that bring innovation and processes. Because if you do not train your people, on something which is going to be futuristic, you will never know how the things are going to change, and you will not be able to know the value of loss that you are going to make over a period of time. So, buying only latest equipments and willingness to do better is not good. Get your trusted team trained and how to use them and also retain them, because many times what we have observed, people who get trained on something very specific also like to kind of immediately write in their LinkedIn account that I know now I know this thing, and then they immediately jump to somewhere else, quite likely. So, for all the industry owners, this part is very important. How do you retain them? So, make a loyal team in your own groups and so on. So, I will just close the first part. This was just only the introductory thing. I will stop this and around 15 to 20 minutes I will take this second part, and then is there a break in between or there is no break, right? Okay. You really want them to sit continuously for a long time? We will see. Okay, all right, fine. Okay. So, let me begin with some basics of flow reactor, because I know that many of you have attended many conferences, you have seen the flow reactors in ACHEMA kind of and CPHI kind of exhibitions. You also directly use some of these things, but I thought that since Professor Chinmay told me to have a basic training course kind of thing, I thought that this might be a very useful thing. I might skip some part of it without getting into too many details. Okay, what I will cover: basics of ideal reactors, why do we need batch operations, important issues in the batch operations, advantages, limitations, and then basic reactor design and why we should go for a continuous reactor. So, typically the batch reactors, I do not need to tell you, we do all cooking at our home in batch mode, whether we were making a cup of tea or any curry or anything, it is all batch. And every day we know that the tea does not taste the same, but we forget that, we do not compare, but if we really have some kind of way by which we monitor the taste of a tea, every day you will get a wide distribution over a month almost every time you do it. So, batch reactors are stirred tanks sufficiently large to handle full inventory of the complete batch cycle, and people typically want to produce as much as possible in a single reactor. Primary purpose is that in one single go you produce large batch, so that then your utility cycles also remain intact as per your requirement, your manpower kind of it should match with your 1 or 2 or 3 shifts at the most. There are a lot of kind of supply chain issues also related to that. You also want to make sure that it is not just the reactor, but further separation, maybe distillation, filtration, washing, etc., all are kind of coupled with each other. So, time cycles of each are set such that your batch time should match with what you really want, and that is a good thing. People kind of that's in general industry has practiced and optimized that. Continuous reactors are generally smaller than batch reactors, and they handle the product as flowing stream. So, whether it is a stirred tank reactor where continuously feed comes, it is stirred, the product comes out. Basically here the temperature is maintained at a given value, and you monitor that, because depending on that the reaction rate will be decided. In a plug flow reactor, it is like a tubular reactor, feed comes in and it flows, and at the outlet you get the product. The big difference between these two is that in the CSTR, as the reactants enter, they are entering and mixing with the reaction mass which is already there. So, you have partly, say let us assume 60% of it has got reacted, 40% is unreacted, you are adding some more unreacted material to that, so it is becoming diluted. So, as it becomes diluted, the residence time, the reaction time required for completion of this reaction is much more. So, single CSTR can never give 100% conversion, because always some part of unreacted mass will come out. While in plug flow reactor, since the material flows continuously from the inlet to the outlet, the reaction continues and you generate there is a possibility that you can go to 100% conversion depending on the reaction kinetics. There are advantages and limitations of each types of reactor. It is not that kind of one size fits all or batch is the best or continuous is the best. Depending on the type of reaction, you need to choose the right kind of reactor. So, typically the reactor design needs or making a choice depends on a variety of parameters, like volume of the reactor, batch time versus the residence time here, the heat duty for a batch versus the heat duty for continuous, and then eventually the design equation one has to use. Now, typically what happens, the volume of a continuous reactor is always smaller than the batch reactor typically, but it is only between the batch reactor and the plug flow reactor. If you want to get the same conversion for a batch reactor as the same conversion for a CSTR as in a batch reactor, your CSTR volume has to be very, very high, because it is getting diluted, so your productivity has already gone down. Batch time for a specified conversion is typically based on the kinetics, same is applicable even for the continuous reactor also. This is the most important part, the heat duty for a batch reactor. As we start a reaction, you might have seen in your log sheets, initially temperature is very low, then you can keep on heating it for some time, or till your addition is complete you keep certain temperature, then you kind of do the cooking part and run it for some more time at a different temperature. So, with time the heat duty continues to change, while for the continuous reactor then it is a steady state reactor, so nothing changes. So, what is required to make a process continuous or a reactor continuous, you must need to know the heat of reaction. So, irrespective of whether you want to operate a reactor in the batch mode or a continuous mode, heat of reaction is absolutely important, and then you use the design equations for that. So, I do not need to say all these things because batch reactors are already known to you. People have been kind of industry knows why you are using, how do you select the impellers and so on. So, I will just move from this. This is one important part. Typically when you design a batch reactor, it is always typical when the chemical engineers study in the undergrad and use the design equation, it is always about you achieve certain conversion in a given time and so in a given volume and so on. But the economics of a batch reactor is very, very important. So, when assume that your reaction is just now over, and so basically you have just emptied your reactor. So, this is a time you are having an idle time in the reactor where you are kind of washing the reactor, preparing for the next batch. Then the next is the preparation of the reactor. You are basically kind of cleaning it from inside, you are using the air jet to remove everything from the reactor, checking utility temperature and so on. Then the next is you are feeding one of the reactants and using utility to bring it to a certain temperature, and then you start adding the next reactor, either it is a semi batch or batch mode, and the reaction starts happening. Now, basically this particular line indicates that with time how much money you are losing, because when it is idle and not being used, you are losing. It is like an aeroplane. When it is in air, it earns money. It earns money. When it is on the ground, it is not earning money. So when the batch is being prepared, batch is empty, etc., you are not really earning. But when the reaction starts, as the reaction proceeds, you are earning money, and the time decides how fast you earn that money. So your shorter is the batch time, you are going to earn that money much faster, and so that depends on entirely on the reaction kinetics. So what it means is that as the reaction starts, you start earning money, and so faster you earn money. So this anybody would like to reduce this time and reduce this time also, so that you carry out as many batches as possible in a very short time, and so on. So depending on your rate of reaction, because in a batch your heat transfer area is limited, you can't, because you can't carry out a reaction very fast, it will have its own effects. It will generate side products, it will add you a lot of cost to the separation and so on. So depending on how you carry out your reaction, this time where you should stop the reaction to get the maximum profit will be decided. Now all this is okay for a batch, people have been able to do this. So, but then you can't really minimize this time, this is like a loss of time, huge amount of time you are losing every time between the two batches. Somebody might say, now I have 10 reactors, and but cycle has to be followed, you cannot bypass a cycle, you have to have some drain time is there, some preparation time is there, some cooking time is there, and then there is a reaction time. So you are losing time in general. So why to do all these things? You better make it continuous. So the advantages are like, there are several advantages that you already know. There are many disadvantages of the batch reactors, but it is not that every reaction needs to be made only in continuous. There are several reasons for which batch is also necessary. There are several reasons for which continuous has to be made. So how do you make that choice? That is what we will try to see. So again CSTR, let me go I will just skip some of these introductory. This is like CSTR, as I told, it is the reactants enter, they mix with the reaction mass, because it get diluted, the reaction rates are lower as compared to a typical batch reaction, and so it takes much longer time to complete the reaction. To get the same reaction time as in a batch for a CSTR, it is necessary to have multiple CSTRs in series. So if you have 4, 5, 6 CSTRs in series connected to each other, then this effect can be eliminated. So then you get exactly the same time as in batch, but still make it continuous. And then the plug flow reactors, as I said, like the reactant center, product comes out, what you manage is the temperature and a good mixing. Now depending on whether it is the liquid-liquid, gas-liquid reaction, accordingly you need to have the internal arrangements made in the reactor. Let me just skip this. Okay, well, 1 minute. Okay, so if anybody is doing a isothermal constant temperature reaction A going to B with this kind of 1 minute per second reaction rate constant, and at this concentration, using the rate constants etc., we get the design parameters. So idea is to get kind of 99% conversion in both the reactors, CSTR as well as plug flow reactor. To do that, and my volumetric flow rates are like 60 liters per minute, I am keeping the same volumetric flow rate. But to get the same conversion with the same volumetric flow rate, I need CSTRs which should be kind of 5950 liters, but I need only a plug flow reactor of 276 liters to get the same conversion with the same flow rate and at the same temperature. If I change the temperature, the numbers will change, but this ratio will more or less remain the same. And if you see here, so single CSTR will need 22 times larger volume than a typical tubular reactor. So it is necessary to make that choice. If you, when you should go for a CSTR, when you cannot go for a CSTR. This is the same thing but in different form, and there are some heat effects etc. Let me just, yeah, this is an important case study. So when you do any kind of exothermic reaction, typically if you start the reaction at around 27 degrees centigrade is the feed temperature, and if you do a batch, suddenly the reaction temperature will rise to almost more than 90 degrees centigrade, because it's an exothermic reaction, you added both together. Obviously the reaction is not going to say, okay, no, we will wait for some time before we slowly release the heat. No, reactants will react and then the heat will come out. So if you see this, within 1 minute it reaches almost close to 90 to 93%. It may go to completion also, but not in the desired manner. It will generate lot of byproducts as well. But if you do a slow addition in the semi batch mode, which is a typical industrial practice, that you slowly add one of the reactants, then you can go from 27 degrees to as much as 37 degrees centigrades in 10 minutes time, and then slowly it will come to kind of lower temperature, the reaction will go to completion. So, as compared to your 3-4 minutes reaction time which was the previous case here, that here the reaction got over almost in 5 minutes, but with lot of byproducts. In this particular case it will take 30 minutes and you may get the desired product. The only thing is that the time that you have used and the to make sure that the reaction temperature does not rise to this number beyond this, you have to control time as well as temperature both. So, operational cost increases. In place of that, when you use a CSTR with proper configuration of the heating cooling systems etc., it is possible to, I will not go through this thing, let me skip this 1 minute, sorry for this, I think I skipped one slide. Let me tell you one thing. Okay, if I do a CSTR, what will happen? You will have series of 3-4 CSTRs in series. We do exactly the same thing, reactants together enter into this reactor, outlet will go to the next one, then the next one. Reaction will be, temperature can be maintained at the required temperature of 30, 35, 50, 55, whatever that is required, and still you continue to get what you want. So, it is, you are able to still control the reaction temperature properly. Only thing is that your volumes will increase because your heat is getting distributed. You are not doing it at one location, but you are adding the reaction mass at different locations. Let me go to this part here. Okay. Now, comparison between a CSTR and plug flow reactor. This is something which is very fundamental. Concentration in a CSTR is uniform throughout because you are stirring the entire mass. So, everywhere the reaction is homogeneous or the reaction rate is similar. On the other hand, in a plug flow reactor, the concentration changes along the length of the reactor because you are initially at the inlet concentration is very high. As the reactants move, the concentration decreases, and so your rate of heat generation also decreases, and so your product concentration increases. Concentration in the reactor is same as the outlet, that is for CSTR. In plug flow reactor, high concentration at the inlet, low concentration at the outlet. Here the rate is uniform in the reactor, entire reactor. Here the rate changes with the location. Here the heat duty is uniform in the reactor, that is the rate at which heat is generated. In this case, the heat duty decreases along the length of reactor because heat is more generated at the inlet because concentration is high. At the end, it is it decreases toward the end. So, whenever you design a reactor, whether CSTR or plug flow reactor, the most important thing required is kinetics, reaction kinetics, which nobody measures. I rarely seen any industry measuring reaction kinetics, finding the rate constant and doing the design, except for in some pharma and some fine and specialty chemicals for very large scale manufacturing. Otherwise, nobody, you replicate what is successful in the batch in the lab scale. So, there are few specific advantages and disadvantages of both. Operation point of view, in batch the changes occur in concentration of materials over time. In continuous reactor, at any point of time you take a sample from a CSTR, it is always the same, or in a plug flow reactor, right? From given location you take out a sample, it is always the same because steady state. Type of material, batch can handle all kind of materials. For continuous reactors, it is easier for material which is flows. Then type of reactions, is kind of batch is, you have to slow down the reaction. You can't afford to do heavy exothermic reactions in a batch. In continuous reactions, due to small volume, fast reaction exothermic reactions can be handled. Mixing, due to large volume, mixing throughout the vessel is very poor because you need to have the right combination of impellers. That is also one more thing. Typically, the industries, kind of I have seen in one industry when I was visiting, they had shut down for kind of some audit was going to happen after 3 weeks. So, they are preparing for the audit. So, they are cleaning all the reactors from inside. They showed like, okay, we will show you our large reactor. So, they had a reactor which was like aspect ratio was 4, that you have kind of height is 4 times the diameter. So, they showed, I will show you what all how we are doing efficiently we are doing the mixing. So, we went, it was like a 2 meter diameter and 8 meter height reactor. So, we went through the stairs and I saw from there they had 13 impellers inside the reactor. So, I asked them why, and there was no sequence of impellers, there was nothing. So, I asked them, why do you need this? No, you put more impellers, mixing is better. Then I asked them, what is the reason behind this combination? It's like कुछ फर्क नहीं पड़ता है, वो दूसरा प्लांट में नहीं यूज कर रहे थे इसलिए इधर आके लगा दिया. It doesn't work like that. So, if you want good mixing, you need to have the right combination of impellers, and there is excellent variety available now. There are a lot of good people who know what impellers will be used if you want to reduce the power consumption, if you want to improve the mixing and so on. And then controlling point of view, the controlling the set of actions, like simple control batch, you can monitor the things pH, pressure, etc. in relatively easily. In continuous complex system control systems are little complex. You need to have reactor conditions more little difficult, because you need to maintain the constant temperature profile. I am not saying constant temperature, a fixed temperature profile has to be maintained from inlet to the outlet. So it becomes little complex, but that investment is worth, because once it starts that way, you do not need to stop the reactor. It will continue to, so far you keep giving the same feed, it will always keep giving the same product. Product point of view, extraction of material is only after the reaction. Here continuous extraction of material is possible. Quantities produced are preferable when production in small quantities. For large scale production as well as small with efficient reactors, you can even do continuous. Product development stage, typically you should always do a batch before you in the lab, before you go for even continuous reaction, even at the lab scale. There are a lot of reasons for that. I will come to that point little later when we develop the approach for doing any reaction. If a gas is evolving, if something is getting precipitated, if a solvent is evaporating because of the heat of reaction, because the volume is decreasing continuously, all these things can be monitored only when you are doing a batch. There is no point in doing a continuous reaction straight right in the beginning unless the reaction is extremely fast. Yeah, this has already come. Let me just go ahead. So selection criteria, typically batch is suitable for slow reactions where the reaction time is of the order of few hours, and if back mixing affects the selectivity, if the reactant and product is mixing together again and again and creating more side products, then batch is suitable for slow reaction. CSTR, slow reactions if back mixing does not affect the selectivity, kind of there is only one product, there are no A going to B, B going to C, kind of say nitration, dinitration, trinitration, or chlorination, monochlorination, dichlorination, trichlorination, those kind of reactions are not there, then CSTR is okay. Fast reactions, if the reaction time in seconds, but only if the mixing is also really good, then CSTR can also be used. I have seen a reactor which was not more than 1 liter volume with a proper kind of 2 impellers being used in that CSTR, operated at 120 bar and 300 degrees centigrades, reaction time was 13 seconds, exact 13 seconds, because they were getting the product at the outlet, quench the product immediately, because even 1 second extra it produces stays there, it was producing the derivative. So if you are able to do that, and that does not need, it was not kind of it was not a very exothermic reaction, it was endothermic reaction, but the temperature required was very, very stringent, and so a single CSTR of like 1 liter jug was producing in 13 seconds 1 liter. You imagine what was the throughput then. Flux flow reactor, fast reaction if the back mixing affects the selectivity, and exothermic reaction because it allows you to give very high heat transfer area as compared to a typical batch reactor. So what I am going to do is that I am going to kind of sensitize you all on a few points, very important points, because see, I am sure that all of you are exporting chemicals to Europe and US. They have adopted that, they are going to, the European Union has decided by 2040 they will go to net zero, and by 2035 manufacturing industry will go to net zero, and within that by 2030 the chemical industry will go to net zero. Now that's a very huge challenge, because this is right now we are already ending 2023, 7 years you can't, it's very difficult to likely to go that net zero, in the sense you are using green hydrogen, that is hydrogen which is produced from water, not by reforming, you are using energy or electricity where you are using that hydrogen from fuel cell to the electricity, you are not using the fossil fuel and so on, and the chemicals also that you will be using, majority of them will also be produced using these. Now there are 3 types of emissions: direct emission, indirect emission, and the end user emissions. Direct emissions are what they are committing to reduce by 2030. Indirect emissions by 2032. Direct means what they are producing at their end. the emissions that they want to basically decarbonize the industry by 2030 completely. No greenhouse gases, no carbon dioxide will be emitted from those industries. By 2032, indirect emissions means the other European countries from companies from where they source some material, they would also reduce that the carbon also. By 2035, vendor end emissions basically means all the suppliers of chemicals or any other machinery etc., which is coming to Europe from anywhere in the world, they also should go to the net zero conditions. If you do not go to that condition, they are not going to import anything from you, and this is what they have decided in and passed and this resolution in their parliament, European Union Parliament, which has put a lot of pressure, which means that for our industries to sustain and hand over the industries to the next generation, we cannot continue the current practices. Your industry, because sustainability is no more a word to hear, it will come in practice, in reality only. And when you look at that, why I said that when I come to Gujarat and I meet people who smell money, because they know how to make money from almost everything. So why I said this, because when you look at this sustainability, it is not just making chemicals. There are a lot of things where there are opportunities there is going to open up, lot of opportunities, and all in chemical sector, not just fine and specialty chemicals. Because when you say you need green hydrogen, you want to do the water splitting, it is going to be a photochemical reaction, you need or electrochemical reaction, you need a catalyst, that is a chemical. So, there are a lot of new things which are going to come up, and a lot of changes are already happening all over the world. So, somebody has to keep an eye on that. If we do not do anything, sometime in 2030 all of you will hear from them that in 2 years please confirm that you have gone to net zero, and we will not be prepared, because 2 years is extremely short time to do any such thing. So, it is necessary to make that start moving in that direction right now. There are many ways of doing that. First is make your processes continuous, so that your energy footprint goes down, processes become efficient. Second is eliminate solvent as much as possible from your reaction, that is second thing, because then you are not emitting that much CO2, because when you use any solvent and the reaction happens, let us assume that you have excellent solvent recovery system, you have excellent reflux and recovery system, distillation beautiful and so on and so forth. No distillation, no solvent recovery system is 100% foolproof. You will at the most get 95, 93, 92, 95, 90%. So, it means that 10% of the solvent is always going to the atmosphere, either in the volatile organic compound or in the effluent, and when you replenish that with another 10%, again that 10% is going to go. So, in general all the solvent is going to go in the atmosphere, so that will not be accepted. So, there are a lot of reasons why we have to take this sustainability very seriously now. So, I gave the so I felt like I should talk it like necessity, urgency, opportunity and challenges. There are necessary things, there are urgency behind doing this, there are opportunities to get into this, business opportunities, not just because I am saying business opportunities and challenges. So, and there are excellent challenges which will also open up new business opportunities. So, let me go back a little bit. I will just, so I will take, I promise you I will finish at 5:30, okay, otherwise I will keep on talking. Okay. So, if you go back a little bit, the chemical industry, beginning of chemical industry in India happened through indigenous efforts by few people. First is Professor P.C. Ray from Calcutta University, through Bengal Chemicals and Pharmaceutical Works in 1892, that was the first time it started. Then Alembic Chemicals, Unichem, Chemo Pharmaceuticals, Zendu Pharma, Chemical Industrial and Pharmaceutical Laboratories, we know it is CIPLA, that is the full form of that, and East India Pharmaceutical Works, they all started between that time and the freedom. We got freedom in 1947. That was the time when all these chemical industries started. As of now, there are 11,000 chemical industries in India. 11,000, small, medium, large, micro, mega, etc., etc. You put all together, 11,000 companies are there. And the market size is like 178 billion US dollars. That is the number as of now from the Invest India website. And we aim to expand. So, the China plus policy or lot of investment is happening in India. New sites are opening like Saika, Panoli and so on and so forth. Like people are kind of crazily buying land here and there to put up some or the other plant or replicate the facilities and so on. And new brownfield plants, greenfield plants are going to come. But if we do not change the way we are making it now, or if your new plants are not going to be different than what you have right now, we are not going to sustain for long. So, it is necessary to make that change happen. So, there are 4 points: necessity, urgency, opportunities and challenges. I am going to take these two together because this was necessary now. The necessity was there 10 years back, and that time it was not urgent, but 10 years nothing changed. So, now necessity and urgency have come together, because if we do not change now, then probably we are going to lose this opportunity also. So, I am going to take these two together. So, if you look at your own processes, largely the agrochemical dyes and the fine chemicals where you do chlorination using thionyl chloride, sulfur chloride, bromination reactions, nitrations and so on. So, basically many old processes, conventional routes, large amounts of solvents are used, significant downstream processing is used in terms of recovery because lot of impurities are formed and all. It produces large quantities of waste. For dyes you know your numbers, for pharma also they know numbers, and many times the pollutants are not treated, they are left into the ETPs, CETPs so called, and then it enters into the normal water. Operations are based on toxic materials, huge inventory. If you go to areas, the pharma concentrated areas in Hyderabad, I had been to an industry sometime in June 2000, it was July 2018. We were sitting somewhere and then the rain was about to start, and then the fellow, I was talking to the very senior manager of a company. It was a small company, it was not a large company, it was medium scale company. About rain, then he told his person that this, he gave him a big sheet of plastic and I told him kind of वो नीचे रखा है उसके ऊपर डाल दो. Then I asked him what is why, इसलिए नहीं वो सोडियम रखा है. So then look at the way kind of, so they had stored sodium in different buckets in the solvents, and it was like covered with some kind of a some cloth, and they knew that it was about to rain. So ठीक है, so because पानी के साथ आएगा तो आग लग जाएगी, so you put this plastic on that. And I asked him how much it is, but ज़्यादा नहीं है, 3 ton रहेगा. So you imagine 3 ton sodium at one location. So we can't use the huge inventories which are kept. Like he said, like I got it at cheaper price, so I purchased as much as possible. That was right, nothing wrong in business point of view. That nothing wrong. Okay. Market shares for all our industries, like all these industries on the right hand side which I have listed there, the market share is not significant. When I am saying market share in terms of the actual financial market share, pharma 2.3, dyes 7.6, it might be around 8%, 8.2%, paints is 6.5% and so on. But in terms of the volumes, India produces 26% of the world's pharmaceutical medicine volumes, but market share is only 2.6%. So value is not there to that extent. There is a potential to double the market every year, 5 years, so which means that we can put lot more plants, and a lot of people are getting a lot of money, so it is always possible. The solution to kind of, while we do this, if you have to sustain, we have to revisit the chemistry. Like if you are doing diazotization, I am sure that all of you are using sodium nitrite in some or the other way. Why do we need sodium for that? Where does sodium go in the end? It is not a part of the reaction, it does not take part in the reaction, it does not, so eventually you have to neutralize, make a salt out of that, it will go as a solid waste. So revisit the chemistry, we do not need it. Why do we need it? Thionyl chloride. Chlorination, chlorine gets attached, 1 mole of HCl gets generated, 1 mole of SO2 gets generated. What do you do after with that? People scrub HCl, people also scrub SO2 separately in caustic, over. So you make 35% HCl from that, use it for something, your sulfur what was generated goes in sodium sulphite. again has very low. So, you are actually reducing the value of the thionyl chloride significantly. So, what is required is to revisit the chemistry, re-engineer the processes by crossing the barriers of length scale, time scale and operating conditions, eliminate or reduce the need of your downstream processing. If you produce exactly what you want, why do you need to go for distillation? You do not need to go for distillation. Or if you are able to avoid dinitro products, dichloro products, dibromo products, why do you need to go for further separations? You restrict at monobromo and develop sustainable processes and chemistry as well. So, globally if you see, there are many companies who make these continuous processes like Continuous Pharma, Snapdragon, there are many companies are there, and there are, so all these are the startups from US, and there are many startups in India also, in other European countries and Japan and Russia also, China and so on. And there are many pharma companies who have their own manufacturing facilities, R&D scale facilities based on the continuous processes. And then there are consortium, like in University of Graz there is a flow consortium in Austria. In 2024 October there is a international conference on microreactors where all these companies will showcase where do they stand. So, I encourage many of you to attend that actually next year October 24 in Graz. Then there is Continuity Pharma, it is a portable kind of units for continuous processes. Then there is SRI International, I do not know if how many of you know this company. SRI International is the largest technology based company in US, remains little isolated because they make everything right from an ozone generator to missiles, like hugely deeply involved in almost everything which leads to technologies. Then there is Virginia Commonwealth University, where there is an institute called Medicine for All Institutes, Medicine for All, M for All. So, kind of it is an institute where Bill and Melinda Gates Foundation and pharma companies have sponsored that. Then there is a company called Flow Corporation. So, this is like more like a PSU from USA, public sector unit kind of thing, largely funded by the government to make technologies for manufacturing generic chemicals, generic medicines in US. So, so that your import dependence on India decreases. So, last year they were given $490 million to develop technologies, and they have already kind of started production for certain molecules. And then there are kind of multiple companies who have their own consortium or so on and so forth, and this landscape is increasing. Japan has now a new forum of 35 fine and specialty chemical industries who have specifically decided to come out with technologies that use chlorine, bromine, iodine and fluorine. So, they have decided that we are going to make it all continuous. So, 35 industries have come together, they do not want to have any imports from anywhere else. And in India there are again a few startups are there who are supporting the Indian industries like Amar Equipment, Shavati Engineering, Technoforce, MaxSpeed. So, all kind of people whom you will see in many exhibitions and so on. And the NCL has, we have some work, IICT has started something, IICT Bombay also has many tools and so on. So, and there are, as of now there are 250 Indian industries who are in this business to make batch processes into continuous processes. So, can we wait for long? I do not think we really can wait. This question is irrelevant now, because it is necessary to have clean processes, clean plants. I am sure that your next generation will not accept the plants that you are having right now. They will, because they have seen malls, they have traveled all over the world, they have seen better things. They would not like to enter into the plants which are like you smell acetic acid everywhere, or you start kind of seeing kind of a different kind of a color every part of the plant and so on. So, smaller footprint, green synthesis, zero liquid discharge as well as no discharge plants, energy efficient processes, processes with renewable chemicals, solvent free processes, and get people trained for next generation technologies. So, all these things they are absolutely necessary, we can't really wait for those things. So, necessity and urgency both have come together and we really can't bypass, because if we do not do it now, somebody else will do it better, and then you can't say that no, we will still try to adopt. No, it is not, the time has gone. The moment Ammonia announced that they are making atmospheric ammonia, it has already shaken up majority of the ammonia manufacturers all over the world, because itself they have already talked to 67 fertilizer manufacturers all over the world that they will supply turnkey manufacturing plants at atmospheric conditions, and they have shown how cheap it is when you adopt to their technologies. If that happens, you imagine what will happen to RCF may survive because it is a PSU, other companies you may not know what will happen to them. Same will happen for all bulk chemicals, it is all going to change. Everybody is going to adopt to electrochemistry. So, opportunities, now opportunities are in different spaces, okay. This is where I want you really to focus. First is physical space. Physical space means process equipments, uh, backbone infrastructure of continuous plants, modular plants and the skids. As of now, although I showed you many companies exist who are doing some little bit of their own continuous processes, continuous reactors, etc., we do not see a big, like we have not seen a cornering of India, no, it has not happened, or we have not seen kind of a UOP of India where they are supplying a turnkey plant for any process that you say, it is not there. So, in terms of process equipment, still there is a space. There has to be somebody who will kind of say that yes, we are the monopoly and we are into this, not just in the reactors, distillation column, distillation, crystallization. You will find multiple process equipment companies all over India, multiple are there. All of them do the same thing. It is just that they are distributed everywhere. So, reactors, static mixers, compact separation devices, all are required. There is a concept called rotating distillation column. How many of you have heard this? Rotating distillation column. So, there is a company called Sasol from South Africa, which basically has changed all its one of the oldest chemical manufacturing companies. They have replaced all its distillation columns above 5-meter height by rotating distillation columns, and they have shown that a column which was almost 20-meter tall can be replaced by a column which is 2-meter tall. Now, you imagine the amount of your overall pressure drop required for the vapors to go to the top and the liquid to come down and operating such a large column and so on. They have already reported that their OPEX has gone down by 6 times, not 6%, 6 times the OPEX has gone down without affecting the separation at all. So, new process tools, nobody is looking into this. So, there is a space. So, somebody has to, if anybody you know here who is a good friend of who knows a good process engineering company, look at, do not just fabricate the devices, try to find out can you make like annular centrifugal extractor. Not many people use it for the reaction, even extraction also. Europeans use large number of annular centrifugal extractors that are exported from India than any Indian company, but it can be used for the reactions also. Backbone infrastructure, this is the major thing, dosing pumps. For lab scales, we do not have anybody who makes lab scale piston pumps, which can withstand 10 bar, 20 bar, 40 bar. The number of piston pumps which are imported, if you find from the HSN code every year in India, this number is more than 700. You multiply that by 5 lakhs, that the total, that the minimum cost of that pump, even if it is stainless steel pump head. So, there is a huge opportunity. There is a company in Bangalore who is supplying now piston pumps, but the most important part, pump head is imported, and so cost is much more than that pump which you import from outside. So, who will buy such pump? Nobody will buy. So, dosing systems, pumps, second is mass flow controllers. There is no Indian company who makes mass flow controllers. For gases, you must need to dose the gases at fixed flow rates, and it cannot be done anyway other than by using mass flow controller. So, if you know anybody who is good at instrumentation, who can do this, because a single mass flow controller even for 10 bar pressure and a reasonable flow rate of say around 10 liter per minute maximum does not come, even for nitrogen it will not cost less than 60,000-70,000 rupees. In reality the cost is very low, but we do not make it. China has their own MFCs now, there is a blanket ban on imported MFCs in China, they do not import, there is a blanket ban from the government that this HSN code just drop it, if anybody is buying this thing blacklist the company also, they do not do that. So, MFCs on an average in India, although Brooks and Bronkhorst have started assembly units here, the cost has not gone down. So, unless somebody starts manufacturing the MFCs, it is going to be kind of a different game altogether. Peripherals like temperature transmitter, pressure transmitters, thermostats, microwaves, back pressure regulators, except WICA or some, if you look at back pressure regulators, it is either TESCOM or WICA or Equilibar or Zyput. There is no Indian back pressure regulator to that extent. There may be somebody might exist, but not of that quality. So, again one more, and this is a large imported atom. So, that is why I said that this is an opportunity. The next is modular plants and skids in continuous flow systems. Designing such plants, there are not many companies who are there who can envision, like for dyestuff industry, kind of we were working on one problem where we were given a task that can you design a container based, container mounted 5 ton per day azodye manufacturing plant in a single container. So, we had to do a detailed design of everything at every step. How do you do the separation, how do you control the heat, because I need to, volume was fixed, a container, a single container that basically has 5 tons per day plant. So, we need, so there is scope for people who can design such compact skids, there is scope for people who may actually make and fabricate such compact skids. You imagine a container mounted plant that produces say 1 ton, 5 ton, 10 ton for you, how much is the space reduction in your entire plant? It is a significant space reduction. In fact, your storage vessels will occupy more space than the actual plant. Then augmented platforms, basically now this is something which is largely missing in India, although there are a couple of companies are there. Digital twins, it is right now only for large manufacturing, bulk chemical manufacturing plants like petrochemicals, fertilizers, large solvent manufacturers, they are using digital. Digital twin means you are actually virtually creating a plant on your screen and you are running it and you are basically monitoring it in reality. It is not like a SCADA operated plant, it is a plant that you have made before you actually fabricate, and then you basically test it for variety of conditions, that if my one pump stops working or if it gives the flow rate by 10% lower flow rate, how it is going to affect all my unit operations, what is going to happen there. So, we do not exist there. Then use of AI ML, I am sure that all companies have huge amount of data that you have already produced in last so many years from all your log sheets and plants. If you ask somebody to, if you appoint a smart computer engineer or electronics engineer or chemical engineer to go through all your data, you do not tell him what it is, you just give it ABCD some number and tell him that I am looking for the conditions which gives me this set of information, 100% conversion, this much yield, this much impurity and so on and so forth and so on, just give this much. He will create a program that will help you screen through all your thousands of data points and tell you that yes, this is the condition required for it, rather than you keep on trying again and again every time and compare that last June I had got better results, but this June I am not getting better results, season same nahi hai, वैसा नहीं होता है. Then coming to the chemical space, there is huge opportunity for import substitution, like benzothiophene, nobody in India makes it, largely imported. So, there is a huge catalog of such chemicals, almost there are close to 600 chemicals which where import value is more than 180 crores per year. We just import, we do not make it here, and that is an opportunity. If somebody decides, you may find that somebody has some raw material here and there and you will be able to do it actually. And then new molecules and materials, we do not exist there, to be very frank with you, sorry for that, but what was the last time that we invented a new chemical or a new molecule for any application? We make formulations, like companies like Pidilite to some extent, Asian Paints to some extent, and some agrochemical companies, they make some formulations for their end products. But making a new molecule, making new material, we have not seen, making new surfactant, no, we have not seen that happening also. So, this is something where there is a huge opportunity. If somebody gets into this, you need some good chemists, good engineers to work together and so on, and that is because this is the land where 69% of the chemicals in India are made. Then we must need to have a place which looks at these new molecules and new materials also, otherwise we will keep making the same thing again and again. We generally kind of classify the reactions in different ways, like say, although there are many ways of classifying the reactions based on the aromatic functional groups, the substitution that happens, the activity of the individual functional groups and so on. But as a chemical engineer, we look at classification in this manner because it allows us to decide what should be the setup for the experiment when it makes continuous. This exothermic reaction, shock sensitive reaction where the like diazo is typically a shock sensitive reaction, multi-phase reactions where the multiple immiscible phases come together because they do not mix with each other, series parallel network of reactions, fast reactions, selectivity sensitive reactions where multiple products are possible, toxicity of the product is a problem, where decomposition of the reactant is a problem, like further coupling when you do, the one of the reactants can decompose and so on and so forth. So, which I am just going to show you two case studies here. One is based on the ozonolysis, which we have recently licensed to a company for large scale manufacturing of a product. So, ozonolysis is an organic reaction where unsaturated bonds of an alkene and azo compounds are cleaved with ozone. And if alkenes and alkynes, multiple carbon-carbon bonds have been replaced by a single carbonyl group. So, multiple possibilities exist, and using ozone is the cleanest and the green way of carrying out such kind of a reaction. Otherwise, you have to use hydrogen peroxide and some metal catalyst to carry out this reaction, and then basically eventually you also generate lot of effluent. The outcome of the reaction depends on the type of multiple bonds being oxidized and the workup conditions. So, if you carry out ozonolysis, basic thing that ozonolysis does, it breaks a double bond in the either a fatty acid, or if it is a kind of an aromatic acid where there is double bond, it attacks the double bond. So, we developed a process for ozonolysis of fatty acid for producing a product called azelaic acid. Azelaic acid is basically a product that is used in almost everything that goes on our skin. It's right from all dermatological creams, whether it's even borolene, collagen, it gives a kind of antifungal activity. We import 100%. There are many applications of azelaic acid. Excuse me, can you please not record it? I request you not have. Thanks. Okay. So, applications of azelaic acid are many, mainly which goes on the skin, but beyond that it goes in making, there are 18 different grades of azelaic acid. Very poor grade that goes as a plasticizer or as well as a lubricant. The high grade is a pharma grade. The lower grade that what people get has a price somewhere like around 400 rupees per kilo. What goes in the pharma grade is 15,000 rupees per kilo. So, that is a wide range. And it also is used in the sutures by companies like 3M and in the medical devices also, because it makes sure that locally the fungal actions don't happen immediately after the surgery. The reaction is quite simple. You take oleic acid, and when you subject it to ozonolysis, this double bond breaks, it gives an aldehyde. That aldehyde undergoes oxidation further, and then you get this diacid called azelaic acid, and you get a monoacid called pelarganic acid. The cost of oleic acid is $1.5 per kg. The cost of pelarganic acid is $4 per kg. The cost of azelaic acid is at least $8 per kg at the lowest grade. So, imagine $1.5 per kg is giving you two products which are $4 per kg and almost minimum $8 per kg. If you improve the purity of the azelaic acid or the pelarganic acid, the cost increases further. There are many methods for that. People have used lot of different methods for like ozonolysis in presence of tungstic acid and so on and so forth. We did a simpler reaction where you use ozone, then you mix it with acetone water system because you need to have a solvent there. You cannot carry out ozonolysis in water because it will quench immediately. Typically the reactions happen, the reported literatures at the industry scale, people do kind of ozonolysis from 20 to 40 degrees and then increase it the temperature to 70 to 80 with 80% yield at ton scale has been proven, but it takes 14 hours. People use tungstic oxide and other catalysts with hydrogen peroxide at 130 degrees, 89% yield, it has been shown at very small scale, it takes around 4 hours. Other options are like using gold oxide, gold coated on the alumina and so on as catalyst, it takes 4 hours and 20 minutes. We do a neat ozonolysis, our reaction is kind of 100 gram scale, metal free, no catalyst, continuous, scalable, no additional oxidant, it takes 5 seconds because ozone is active. You do not need such a long time for 4 hours and all for that. Second thing, solubility of gases decreases as the temperature increases. So, if you go to higher temperatures like 70, 80, 130, it is not going to get dissolved anyway, it is going to get decomposed first. So, you do not need such a long time. So, we developed this process at the lab scale and then took it from lab scale to the pilot scale. Our conversions were like 99.8% conversion, we got 98.5% pure azelaic acid. If I subject it to one more step of purification, it will cross 99.5%, that is the pharma grade. And we even made a kind of pilot plant which was just like 3 meters by 1.5 meters to make close to 2 kilograms of the final pure crystalline product per day. We subjected the same approach for different fatty acids having a double bond, elacetic acid, ricillinic acid, petrosinic acid and uracic acid. We always produce similar kind of products and all of them have applications either in the veterinary industry or in the pharmaceutical industry. So, basically it took us close to 2 years to develop this process, because ozonolysis is fast, people are not willing to do ozonolysis because the ozonoids have to be quenched. So, if you do not quench the ozonoids, they are kind of catastrophically kind of what do you say, they break on their own. So, if you have water in the reaction, even small quantity, it basically quenches the ozonoids. So, you do not have any way ozonoids will remain in the solution at all at any point of time after the reaction is over. So, we ran the pilot plant for almost close to 500 hours discretely for different grades of fatty acids, because fatty acids, oleic acid also comes in different grades depending on what is the content of your C18-1 plus C18-2. We produced a lot of quantities of this different types of the azelaic acids of different grades and so on. And now, so soon there will be a kind of first Indian manufacturer of azelaic acid that will start the production. Similarly, there was another drug called ivacaftor. I will move little faster here. Let me just move again. Ozonolysis reaction. I will come to this point here. This is the last step. Kind of this is a complete reaction step. The first step is ozonolysis here. In general, this particular step in the batch takes 14 hours at minus 78 degrees centigrades. We do it at 0 degrees centigrades in 2 seconds. That is where the first thing happens. We got perfect selectivity, no further separation is required, and then 2 more steps of the reaction. Now, making this particular drug was very, very important, because I will tell you the reason. This is the world's most expensive drug, $300,000 per patient per year. That is the cost of the drug. And kind of after the COVID-19, there is basically cystic fibrosis. People who have cystic fibrosis, where the lungs become fibrous over a period of time, they need this drug. And after COVID, this basically number increased significantly. And so, the demand for this particular drug also increased significantly. So, we have now a continuous process with a US patent granted, European patent granted for this particular drug molecule. I will skip this case study here. This was I will go to, I will need 5 more minutes. I will prefer to do that. Typically, when you see the literature, you always see a lot of complex molecules, medicinal drugs are reported in the literature. People make all kind of expensive drugs to show that we have done this for the first time, that for the first time and so on. But there are high value, low volume drugs that are sold by the innovator companies like Novartis, Pfizer, Amgen and so on. Nobody pays attention to the drugs that are required for the people who can't afford to buy drugs. So, that goes in the category called neglected tropical diseases. It's like the people who can't afford to buy the drugs to treat themselves. So, who will take care of those? So, there are companies, there are philanthropic foundations like Bill and Melinda Gates Foundation, Wellcome Trust, then the UNESCO is there. So, basically they pay a lot of, WHO is there, they sponsor all these things. So, one such disease is called leishmaniasis. It is a top parasitic disease. It is caused by bite of a sand fly. So, people who stay in unhygienic areas, they basically, when a sand fly kind of bites them, it produces rashes all over the body, and it is irreversible in large number of cases, and many times it is fatal, and almost every year 0.7 to 1 million cases occur annually, and 40% of them kind of basically do not kind of survive after a couple of years, because the infection spreads. So, this drug was invented by London School of Hygiene and Tropical Medicine for anti-leishmaniatic effects. it is called miltefosine. Only one company in India makes it right now. So it goes in the WHO model list of essential medicine for all the developing countries, because developed countries do not need this, it is for the developing countries. And the synthesis is not very straightforward, it includes lot of raw materials which are highly active and reactive. So objective was to make a continuous process for this drug called miltefosine. This is the only oral drug, and develop efficient synthesis process that gives significant cost reduction. And there are a lot of challenges. Every step it forms solids, every step it forms kind of byproducts, reactants are highly reactive, and it is impossible to kind of assume that you can make everything in one single go or one pot synthesis kind of thing. So if you do the retrosynthesis, you start with basically to get miltefosine, you have to start with 1 hexadecanol. And so if you start with 1 hexadecanol, these are the 4 steps which are involved. And typically in the batch, you use lot of solvent at very low temperature, 0 degrees in this case, it needs 1 hour at the lab scale for 10 milligram scale. Then second step also 1 hour at 0 degrees centigrade, third step 60 degrees for 1.5 hours, again lot of solvent, acetic acid is used. And then the fourth step is a solid liquid reaction at 70 degrees centigrade, but with THF under reflux for 3 hours. And when you do the reaction, in all the 4 steps put together, you get around 74% yield. We thought that this is an easy thing to do. We basically then draw, yes, we were confident that okay, this will become easy. What we need is basically kind of 6 pumps, 4 reactors for each reaction to happen, and maybe we will need some separation and all. And we carried out, we planned, this was the on paper plan, and it did not work. We had to go back to each step, literally on each step we spent 2 months minimum, because every time you do the reaction, it either clog the reaction or it will be reactor or reaction will be incomplete. So students had to struggle a lot. So eventually we could optimize the whole thing in continuous. I will not go through details. We start with 1 hexadecanol and basically the POCl3 highly reactive and triethylamine, and the first reaction we optimize the reaction in 8 minutes at 70 degrees centigrade, second step in 9 minutes 80 degrees centigrade, third in 12 minutes 80 degrees centigrade, fourth for the solid liquid reaction with including a separation that must happen, because otherwise the reactant gets kind of quenched, which again happened in 5 minutes. So this was the first ever telescopic continuous, telescopic because we are not separating anything, we are just continuously doing it. Total residence time of 34 minutes as compared to 15 hours in the batch. We were able to make 10 grams of the pure product per day in the lab, 10 per hour in the lab using this particular setup. So what it shows is that the reactions which are highly exothermic like your sensitive can also be done in continuous mode. Now coming to the interesting part that some of you may like to listen to, diazochemistry. I will not go through much details. We have started a large program on looking at reinventing the dyestuff industry, that basically India has a large dyestuff industry which manufactures acid dyes, basic dyes, reactive dyes, azo dyes. We do not have anybody, or rarely we have anybody who makes thermochromic dyes. We have people who make fluorescent dyes. So there are a lot of different types of dyes people manufacture in large quantities, but they also produce a lot of effluent. They also use a lot of energy while doing these things, and the methods of manufacturing are still very, very old. So we have through this CRDTH, for which you all have come here, the effort is entirely to focus on the dyestuff industry. So this is like a project which will run for 5 years, another 3.5 years from now, where we will be looking at working closely with the industries on relooking at the synthesis and manufacturing processes for all kind of dyes. We are creating dedicated facilities in NCL for people to come and use and what we have in NCL, so that we can actually carry out the reaction. We will be able to show you how you do your reaction with sulfuric chloride without using solvent, for example, or how do you basically kind of make sure that you use stoichiometric quantities of the reactants to still get the same conversion and so on, or how you do the reaction without using sodium nitrate. You still do the diazo, but without using sodium nitrate. So all these things we plan to do. We already kind of, I will just skip this whole thing. We already started making many of these dyes, and we also put up a pilot plant now there. So we will very soon start kind of our website will be ready, the facility will be open for everybody. We will approach through GDMA and IDMA to basically sensitize the entire Indian diced up and colored manufacturing industries to take a look at it and allow us to do it. You de-risk your R&D, you do not need to take the risk, allow us to, because we have already taken, we have invested huge amount of money in it. Allow us to do that so that you will be able to see what we are doing and how we want to do this. We have created some facilities over a period of time, and all of this will be available for the industries to use. Let me skip for this. Here are some of the processes which are available at our end. Now I will come. I will not. I will just. Wait. I will give you that. Okay, I will not go through these because typically this will be required when we have a lot of people here, because many times we have design issues, technology absorption issues, then we have operational issues. This is a much bigger one, organizational issues. Like, I will not try first. Let somebody try. I don't want to be first. I will see somebody will tries. I don't want to be first. I don't want to be too late third also. I want to be second. And so everybody wants to be second. There are very few industries who want to be first, and they really go ahead. So that's a syndrome. Then second is why change? I have already done the investment. What is the payback period for my new plant? I have already a plant which is kind of, I have already made all the money from that. So I don't need to kind of reinvest into something new. Will it work in India? It's very expensive. Why should I put a new technology? My plants are already, I am buying somebody else's reactors, I am using it, I can rent reactors and still make money out of that, and so on and so forth. So I think there are operational issues. Once you see such small systems working here or in NCL or anywhere, it will help change the mindset, because it will be for the long term. Please realize that when you see the tip of the iceberg, a lot of effort goes below to make it happen, make it float. And so the time has come that if you want to sustain, we have to put efforts here, so that we see the iceberg, that it still floats and it still survives and does not vanish. So I was talking about all these four. I hope that I have addressed them properly. Let me come to the last two slides. We have started the Center for Sustainable and Continuous Manufacturing at NCL. It is a joint effort to reiterate the same thing, and this will be done through NCL, and there is a UK partner called Center for Process Innovations, where we have three kind of partners: NCL government funded partners, founding partner, then technology partners and the beneficiaries. The plan is to reach out to almost more than 100 industries in the next 2 years who will adopt to many of these things. We are creating separate buildings, separate facilities for that. We already invested a lot of money, and kind of we are creating a digital platform that will allow people to kind of, it will be like an open platform for people to ask for the help, that yes, we have seen this is what has happened, what to do, and you do not need to kind of, no agreements etc., will happen through that. So a lot of things are going to change. You will hear from us on our website very soon about that. So let me just go through this. Yeah, these are all the clients with whom we have worked over the years, and we do conduct training programs for the whole day as usual, and this is summarized. So continuous flow synthesis is the most optimal way of exploring chemistry and translating into feasible process. That is the only future of Indian chemical industry. You cannot bypass that. You have to make your processes continuous. Issues like carryover of the unreacted reactant, bypass, etc., byproducts, etc., they cannot be ignored, but good engineering, good understanding about reaction kinetics will always help. Heat requirement at each reaction step is different. So general perception that chalta hai will not work. You have to, because once it is continuous, you cannot make changes. But the same continuous plant can be used for many products. The hypothesis that I have one continuous plant I cannot use for anything else, that is wrong. If you know your reactions better, you can use the same plant for multiple products. Combination of different types of reactors is not uncommon. So we are kind of, so this consortium has now already started gearing up, and when we take pride in having our own vaccines, our own satellite launch vehicles, our own other systems, why not to have our own flow reactors and better processes also? It all depends on the end user industries, because if you do not use our own things, you will not be able to take pride on that. Thank you very much. This is my last slide.